Now we turn to heap sort. It reuses the max heap from chapter 12 to sort a whole array in place. Chapter 12 built a max heap for fast access to the largest remaining value. Heap sort is exactly that, used to sort a whole array in place. First, we build a max heap from the whole array. Chapter 12 does this in big O of n. Then we repeat one move. Swap the root, which is the current maximum, to the end of the live region. Shrink the heap by 1, then heapify down to restore the heap order at the new root. Every extracted maximum lands in its final sorted slot at the end of the shrinking region. The array sorts itself from the back forward, with no second array needed. Let's read the pseudocode. Heap sort first calls build max heap, which arranges the whole array into a max heap in big O of n that is chapter 12's routine, unchanged. Then the loop runs n from n-1 down to 1. Each pass swaps A at index 0, the current maximum, with A at index end, its final sorted slot. Then max heapify fixes the new root over the heap that just shrank by 1. Notice there is no new sifting logic at all. Heap sort's whole job is calling two chapter 12 routines in the right order. Let's trace heap sort. The top row is the max heap right after chapter 12's build. The root, 16, is the largest value in the whole heap. Each row below is one extract. We swap the root to the end of the live region, then heapify down the rest. First extract. We swap the root 16 with the last live value and lock it at index 5, the amber cell. 16 is now in its final sorted spot, for good. Heapify down then fixes the shrunk heap, and 14 rises to the root. Second extract. The new max is 14. We send it to index 4, the amber cell, and lock it. The live heap shrinks again. Notice 16 at index 5 never moves again. Third extract. The max is now 10. We lock it at index 3, the amber cell. The back of the array is filling with sorted values, largest first. Fourth extract. The max is 9. We lock it at index 2, the amber cell. Only 2 values are still in the live heap. Fifth extract. The max is 8. We lock it at index 1, the amber cell. The last value, 7, is already smallest, so index 0 is gone by elimination. The array is now fully sorted, 7, 8, 9, 10, 14, 16. Predict, then reveal. After the first extract locks 16 at the back, and heapify down runs on A from 0 to 4, which value rises to the root and gets locked next. Pause and answer. The answer is 14, the largest of the 5 remaining, and the second row locks it at index 4. Each extract sends the current maximum to the back, so an n-element array takes n-1 extract steps, each one a big O of log n heapify down. That is big O of n log n overall. This is heap sort in C. The function takes the array A and its size n, it sorts the array in place, using the heap we built back in chapter 12. The first line builds a max heap from the array. Now the largest value sits at the root, at index 0. The loop runs in from n-1 down to 1. Each pass places one more value in its final spot. First, we swap the root with the element at index end. The current largest value moves to its final sorted slot at the back of the array. Then we call max heapify on the smaller heap. The heap shrinks by 1, and this fixes the new root so the largest remaining value floats up again. Heap sort's cost is the same in every case. Best, average, and worst are all big O of n log n, that is n extractions. each in big O of log n heapify down. It is not stable because heap reordering has no notion of original order. It is in place, and it has one real downside: poor cache locality, because heap parent and child indices jump around memory, unlike merge sorts and quicksort's mostly sequential access. So watch out for a tempting conclusion. You may think heap sort is the clear winner, big O of n log n guaranteed, and in place, beating both quicksort with its bad worst case and merge sort with its extra memory. But those index jumps scatter memory access, and the poor cache locality usually makes quicksort faster in practice, despite what the theory says.